Today we've got a couple of really interesting presentations. I think one of them has to do with the concrete canoe presentation. This is the Civil Engineering Department's first year to do this. It's a great competition. It's in the same sort of vein as the Baja SAE competition, in that you get a bunch of universities competing, and it's a lot of fun, a lot of excitement involved with it. So Aaron's going to talk to us about that. And then I'm going to share with you our trip over spring break to Honduras Outreach International to the little city of San Esteban, Alancho, and the foundation work that we did there for in preparation for the bridge, the pedestrian bridge. So,
awesome.
Aaron, you're on.
Sweet. My name is Aaron Carter. Like Forquin said, me and 3 other senior civil engineering students were assigned as our senior project to do the concrete canoe. And ASCE hosts this competition every single year. Our conference was the Southeast Conference, so we traveled down to Chattanooga last week to enter into the competition and race our canoe, and to present our educational experience that we learned throughout this entire year. So I kind of wanted to first give a little background about how we designed this canoe, little engineering aspect to it before I actually go into the competition and what we did at the competition. So just to give you a little snapshot, we broke this down into 4 different components. The hull design is the hull geometry of our canoe, so that gave the basic shape of the concrete canoe. And then we went into the structural analysis, the structural design, and mixed design. If you follow the green arrows, that will show you the layout as to what the hull design gave to the structural analysis, and then structural analysis to structural design, and so forth. So I want to give you just a quick little example about what that would look like and how our iteration process entailed. So the hull design first had the length, depth, and wall angle assumed, and in that they produced the hull geometry. They then gave that hull geometry to the structural analysis, and structural analysis was able to calculate the forces to determine where the waterline would be. That waterline was sent back to the hull design, and the hull design then produced the drag coefficient, tipping angle, and so forth. We used this iteration process throughout the entire process of this entire year. And so I just want to give you a little design aspect of what we did this previous year. So now I'm going to go into what the ASCE competition is. So last weekend, the civil seniors and a couple other civil engineering students, and also other mechanicals and electricals, I think, came with us. And so we went down to the University of Chattanooga, and we competed. And what this competition was broken out into 4 main components that the judges were looking for. And each were, and I'll just describe them right here. So the design paper, the oral presentation, the product display, and the 5 different races. So how the judges came to determine who got first, second, and third was through this process of, I'm going to explain that on the next slide. So the first day, we set up our product display, saw what the other universities presented as well. So we put up everything that we did, and we could see what all the other universities were doing. There were a lot of universities that were there. Every single university you can think of from Florida was probably there. There was a couple universities from Alabama, and there were 3 actual universities that shipped their canoes from Puerto Rico. And that was really interesting because they brought their culture with them throughout the entire competition. So they were hooting and hollering and banging on their drums and having a good old time. It was a really cool experience to just see the spirit of the competition and different cultures combining together. It was really nice. So as I said, the first day we displayed our concrete canoe and everything that we had. Then we did an oral presentation to the judges. And finally, we did our swamp test. Later on, I'm going to explain what the swamp test is. I'm going to show you a quick little video. And then finally, the last day, we did our 5 different races. So how the judges came to determine who got first, second, and third They distinguished them in 4 different components, like I said earlier: the design paper, oral presentation, product display, and the 5 different races. So here's an example. So let's assume that there were 5 different judges, and on the design paper, they had these 5 different scores. So 90, 87, 94, 83, and 90. Overall, those rankings produced 2nd, 3rd, 1st, and 2nd overall. Then they would take the average ranking. So that's the main thing you want to keep in main thing that you wanted to notice was the average ranking was kind of like the driving force that determined who got 1st and 2nd. And that average ranking was about 2.4. And then they would compare these to the overall of all 4 different components. So I wanted to first show you what the swamp test was, because I know a lot of civils know what this is. Well, not all civils, but so this is called a swamp test, and what this is it's determining whether the canoe can be buoyant once the canoe is fully submerged underwater. So while we're racing, they wanted to make sure that while we're racing, the canoe, in case it capsizes and fills up with water, that the canoe can pop right back up so that we're not dragging the canoe out from underneath the bottom of wherever the lake is or ocean. So that was a quick little video. Come on. Here we go. Cool. So I wanted to kind of explain what the 5 different races were. There was the male sprint race, and then the female sprint race, and then also the co-ed sprint race. And I'll just kind of show you our, so what this would look like is you would line up your canoe on the right side, and there'd be 5, yeah, there'd be 5 different lanes for each university. So our lane actually was the first one. So where these arrows indicated was where and how we raced. So for the male and female sprint race, there was only 1 lap required. So we would start here on the right side of the red buoy and go around and then just come right back down. That was it. But for the co-ed sprint, we had to do 2 laps. So instead of just having 1 little turn up here, we had to go down back and have 3 total turns and finish. We actually did really well. Chris Gwaltney just informed me that our girls did exceptionally well. So we're really surprised at how well we did during the sprint race. So how the endurance race looks is we had 1 male endurance race and 1 female endurance race. We would start here in the bottom right corner, and we would zigzag our way through these first couple buoys, and then follow all the way out and around this huge track and then finish. I remember our time for the males was about 9 minutes and 15 seconds or something like that. So we were extremely surprised at how well we did. So here's a video of our race and during the competition. We strapped a couple GoPros on the canoe and also on ourselves, so it's going to look pretty cool. Do this one first. Yeah, it looks kind of awkward, but Ryan was just relaxing, as you could tell, once he finished or whenever he wanted to. I just ran this. There we go. And you can thank Matthew Hall for the soundtrack. And yeah, that's Ryan, just, relaxing. shaking the boat. Cool. Now I'll show the second video. Yeah, that's it on that one. Second video shows the angle on top of my head and also Ruth's head, I think, yeah. So here's this. This one did not have. So you can kind of see the beach and how many people were there. There are a lot of people that were at the competition. Us cranking it out. That white buoy is where we finish. Yeah, this is kind of cool because during this video you'll be able to see other canoes and what theirs look like compared to ours. If you see duct tape on ours, we had to attach more styrofoam on ours in order for the swamp test to be successful. Because originally our canoe sank because our specific gravity was too high, and it's just what we'll work on next year. But as you can tell, we all had a blast. There was a bunch of people there. It was really fun. Go back. And so those are the two videos. And then here are a couple pictures that I took personally that just describe the competition in a little more detail. And the top left is the product display. So here are a couple cylinders that we displayed in our engineering notebook, and report are supposed to be here. I don't know where the other one is. And then, yeah, that's true. We had a couple things go missing during the day, but they showed up eventually. So that's what product display looks like. Here are other canoes. Here's the University of Florida State University, or Agricultural, Florida. This canoe actually sank. It was one of the, or no, it didn't sink, it actually broke. Yeah, it broke in half. And then the University of Miami is right behind them. You can't really see this canoe, but that was the University of Puerto Rico. They actually advanced on to regionals and did exceptionally well. They had an outstanding canoe. And right next to us, this was, which one? University of Tennessee Tech. They did a really good job on their aesthetics and labeling. But honestly, the funny thing is, you're not supposed to have stickers on your canoe, and that's actually against the rules, so they got a little deduction. But here's our canoe in the top right with our product display and stand. Are there any questions?
Now, during the first video you showed from swamp test,
Yeah.
that one they pushed down, it just popped right back
Yeah.
out of the water. What are the rules about, is it all concrete? Except for like...
That's a great question. The actual hope for is to be all concrete. Our canoe, we had to apply more styrofoam in the inside in order for our canoe to come back up. So yes, the goal is to make the canoe fully out of concrete. You can't tell from this picture, but we actually placed end caps that had styrofoam inside the canoe that we encased over with concrete, and that is legal. You're allowed to do that, and there's no deductions involved. But once we failed our first swamp test, we had to apply more styrofoam in order for it to float, and we got a little deduction because of that. But other canoes, so like these canoes here, both of those just popped right back up, or they popped up just enough to be right below the water. Really, they're just looking for the canoe not to sink to the bottom of the lake or wherever it's located. Any other questions? Brad?
You guys, what's the best method you guys came to overcome like drag, like to get the most speed and reduce the water line?
So to reduce the water line and I'm just trying to repeat what you said, and to reduce drag was through the hull design. And The whole design was a continual process, like I explained a little bit earlier through the iteration. So our base canoe looked totally different than what we have here. And it was just through the continual process of applying where the water line went, friction of water forces and the forces along the canoe. That's what enabled us to come up with the optimal average design for all those components. And there was more components than what I listed for sure.
So you had a math model for that?
Yeah.
Did you also do like water tank testing or like simulations of the blue models?
We did not. There is a lot more that we could have done. And that's what we're planning on hoping for next year. So we're looking for more detailed analysis and, like Brad said, the drag forces that you could do. You can have a prototype model and put it in a flume. That's something we could have done. There's a lot of little things, like our specific gravity was really high, so we're wanting a lot more test mixes with concrete. So we only tested with sands, and we really want to be able to, for next year, have no sand involved and just have a bunch of either microspheres, glass spheres, polymers, things like that in order to make the concrete as light as possible so that the swamp test happens and the canoe just pops right back up. Any other questions? Sweet. If you haven't, if you have time next year, please help out, get involved, because obviously it looks a lot of fun. So thanks.
Sure. All right, thank you, Aaron. Yeah, we're really excited about any of the student competitions like that. That really makes a difference. It does. You can really apply what you're learning in class, and to be quite frankly, you learn stuff in the competitions that you won't learn in class. So it's really a good thing to get involved with. Before I get into my presentation, I do want to remind you all that next Wednesday, April 1st, we're going to have a speaker that comes from Wright Industries. He's going to be talking about robotic animation. So that's coming up next Wednesday. And then on the 10th, is that right? The 10th in the afternoon, we're going to have St. Thomas Hospital here with Da Vinci Robotic Surgery will be on campus, and they'll be presenting. And that'll be here, is that right? Or will it be?
I think it's in the Paul Rogers boardroom.
In the boardroom. All right, cool.
He's going to talk about a surgery that he just did. He'll narrate it live, and then eventually bring in their robot. We're going to be able to play with it like we did last time.
Okay.
We're going to do a live telecon with Da Vinci engineers out in California that work in the R&D group.
Right. So
It's like
watch for more details on that. That's going to be really neat. The Paul Rogers boardroom is over in Ezel, first floor of Ezel. It's one of those rooms that we're not normally allowed in. So we'll get to use it for this. Apparently this is big enough that they're going to be let us do this. So, okay. Also, don't forget to get scanned before you leave so you can get credit for this. All right. Now, what I'd like to share with you is the work that we did over the spring break, preparing the foundations and the bridge abutments for the pedestrian bridge that's going to be installed in San Esteban, Alancho province of Honduras. This is coming up in August. Obviously we're doing the bridge build starting today. It's going to be built out on the lawn. We're going to disassemble it, ship it down there, and then in mid-August we'll be going down there to put it in place. And I just want to show you guys where we're going to be doing this and what you can expect to see down there. This is the school. And by the way, Gwaltney's been there already. Chris Gwaltney's been here with me. We went last year to do the survey trip. So a lot of this will look familiar to you, obviously. Wish you could have been there this week. It was a lot of fun. Anyway, this is the one side of the highway where the middle school is. The other across the highway is an elementary school, and these two schools work a lot together. So over on this side, you've got the the middle school. On this side, you've got the elementary school. On this side, you've got the computer lab. On this side, you've got the soccer field. So they share a lot of resources, and they go back and forth. And this highway that you see here, while it's only a 2-lane highway, it's a very busy highway and going to get even more busy as time goes by. This is the main road from Tegucigalpa to what is going to become a major seaport on the Gulf side in a city called Triejo. It'll be the deepest port in Central America on the Gulf side of the coast. So it'll become very, very busy very quickly, and the traffic on this highway is going to get busier and busier and busier. Even though this is a very rural area, we're probably about 6 hours from 5 or 6 hours from Tegucigalpa, which is the capital. But anyway, this is where it's going to be. The bridge will span right here. See this house right here? There's a footer right here, a bridge abutment right here, and it's going to come across to a steel tower on this side with steps coming down from it. And what our job was over the last week was to put the concrete abutments in place. Now these have been designed, the bridge has been designed by, and the abutments as well, by some professionals here in town that our students have been working with. ICA is the name of the company. It's Infrastructure Corporation of America. And their people have been working with us on this, as well as Barge, Wagner, Sumner, and Cannon. So we've got two different consulting firms working on this thing. This is the lower foundation. When we got there, the foundations had already been dug, and they were placed pretty well. You could see where the surveyor's benchmarks were. You could tell that they had lined it up from one side of the road to the other very nicely. And but as with most excavations, it's a little bit bigger than what it needed to be, which just meant we had to mix more concrete to go in there because we wanted to minimize the amount of formwork that we had to use. So this is this was the middle school side. This is the bigger of the two foundations. This is the one that's going to support the tower that supports one end of the bridge. Okay, the elementary school side. Okay, let me back up. This side is basically just sitting on a concrete foundation. This side's going to be on a steel tower, and this is the side that everything's going to be anchored on. So because of that, this foundation had to be much deeper, much bigger, and a lot stronger. So anyway, we're checking the dimensions here to make sure that it's good. And we started filling it with the rebar cage. Okay, now those of you that haven't had reinforced concrete yet, concrete's really good in compression, not so good in tension. Okay, so you can't guarantee that the whole thing's going to be in compression unless you do some really fancy stuff like post-tensioning or something like that. So what we do is we add steel in order to carry the tensile load. So in this particular case, there's two different types of steel. There's the steel associated with shrinkage and temperature change, which is just required by the code. Basically, if you don't put steel right there near the surface, you're going to get cracking simply because concrete shrinks, and you don't want the cracking because that leads to other bad things. And then the other kind of steel that we've got is going to be steel that's there specifically for strength. Now what we're doing here is we're putting in the steel that is for shrinkage. Okay, so in this particular case, it's just going to be a cage that looks like this. This is actually on the elementary school side, and so this is the smaller of the two cages here, and we call them cages because that's what they look like. But the rebar is cut and then wire tied together right like that to form the grid. You've got the bars going in both directions, and so this will go in the bottom of the foundation, and it's minimal steel necessary there to prevent cracking in the foundation. Okay, and it goes in right like this. We had a little bit of a problem here. It was supposed to be square, but there was a little planter right there. We decided, we used a little engineering judgment and said it's okay just to cut the corner off. So we went ahead and did that. This is Daniel Jordan. He's senior civil engineer. He was the one who actually did the drawings for the concrete foundations that we were working off of. So every time we ran into a glitch or anything, it was his fault. So anyway, it was good to have him along because we needed a scapegoat. Yeah.
I'm surprised to hear you say you cut corners on this engineering.
Yeah, we did. We cut corners. Definitely cut corners. Thank you. That's good. I'll have to use that next time. Yeah, that's great. Now, contractor. Yeah. So anyway,
This one we did have to form up. It was going to come out of the ground because it's got to get up above the edge of the hillside here to because it's got to project across. So we raised this about 6 inches above what we expected to. It was dug. The foundation was dug just a little bit too deep, and we also had to put the formwork there in place as well. And as we came up with the cages, you can see what's happening here. This is the second layer of shrinkage steel right here. Okay, and then what you see standing up here, this is actually the reinforcing that goes into the pedestal, and I'll show you as we go along. You'll see what I'm talking about here. So basically, you've got a mat foundation, and then you've got another rectangular projection of concrete up that becomes the pedestal, and that's actually what it sits on. And this is designed to carry any bending that might be in the concrete, as well as to handle the shrinkage problems. Okay, and then this is after we poured the mat foundation. You can see our formwork here. This is the formwork that's associated just with that first pour. We had to do this in 2 pours. Not my favorite way to do it because you might have a cold joint between the two. It's really better off if you can do it all in once. But we were setting a lot of concrete, and because of that, we had to do it in 2 different pours. So if you got to do that, then the best thing to do is to go ahead and pour the mat foundation first, and then we'll come back and we'll do the pedestal the next day. And then this is on the other side. This is actually this is out of place. Hang on, let me go on. I'll come back to that one. This is the other side now. We went across and started work on the larger of the 2 foundations over on the middle school side. And here we've got the cage leaned up here, and everybody's tying away, getting things ready. This gentleman right here is a fellow by the name of Daniel Toon. He works for a construction firm out of Atlanta, Georgia. He's their chief engineer, and he was our concrete guru on this one. And once we get all the cages all the steel in the bottom of the foundation, you got to kind of crawl in there with it and get in the cage to finish the tying. That's what Luke Burris is doing here. And then we poured the mat part of the foundation. Once again, this one didn't require any formwork. So we were able to pour the concrete in here just like this. The steel that's sticking up here is the steel for the pedestal foundation as well. Okay, so now we've got 2 pedestals that we have to pour. And before we do that, though, we've got to get in there and we've got to set the anchor bolts in their proper locations. This is the most critical operation that we did the whole time. If the anchor bolts aren't set right, there are 2 things that will happen. One is when we go in to put our base plates in place, they won't fit. Okay, so that's one thing. So we've got to be able to have these things positioned properly from this set, this grouping to this grouping. That relative position needs to be accurate. Okay, the way we did that was we had aluminum plates made that represented the base plates. Threaded our anchor bolts through there, and then we've got these 2 straps coming across here, and that was machined in such a way that if we got this all assembled right, it would automatically cause those 2 groups of anchor bolt patterns to match up correctly, okay, relative to each other. Then we've got a second problem. The second problem is as we sight across to the other side of the road, we've got to be sure and hit the other pedestal. If we don't hit the other pedestal, we haven't done our job. Okay, so that's what Daniel's doing here. We're sighting across to a line right here in the middle of this plastic plate that I showed you earlier, that represents a line connecting the two bolt groups. We'll set the angle to 0 there, and then we turn the total station 90 degrees to sight across to the other side, and that tells us whether or not we're hitting the other pedestal. Well, it took a lot of adjustment to finally get that, and as a result, and you can't see it in any of the pictures. The foundation is about like this. No, I guess the foundation's about like this, and then the anchor bolt pattern is skewed a little bit on it. Okay, but that's in order for it to hit. Doesn't really matter, but it doesn't look the best in the world. So, there again, contractor problem. Okay, here's our anchor bolts here. This is an addition that we added to it here. The design did not call for any kind of reinforcing to tie the anchor bolts into the rest of the foundation, but we felt like it was a good idea. This is not uncommon practice. It's nice to have this steel in here so that if the cone of failure coming up from the base of the anchor bolts you start to get any cracking, you've got this steel here to kind of stop it. So we added that to it with the blessing of the designer. We talked to Carter about it, the fellow back at Barge Wagner about it. And then this is after it's in place. As you can see, our anchor bolt pattern in each of these is good. The plastic plates fit right back on it. I breathed a sigh of relief when I saw that, because I've been on a few construction sites, and I've never been on a construction site where the anchor bolts were right. Okay, invariably you had to chip them out, move them over, take a sledgehammer to them or something to get them in place. So we back up. Here we go. Okay. So first thing we did was we put the plastic plates on there, and sure enough, if the plastic plates goes on there, then that means that the base plate will fit. The other problem is, do they line up properly? Are they square with each other? And we took measurements. One way to check that, there are two ways to do that. The easiest way to do it is I took a tape and measured from the outside of that bolt to the outside of the diagonal bolt over here and compared it to the measurement from the other one. Those two measurements should be equal. If they're equal, then they're square with each other. And then the distance, the center distance between the two was measured from the center of the hole to the center of the other hole, and it was dead nuts on what the drawings called for. We're going, great, we've done a fantastic job. And then we did the same, we repeated the thing with sighting across, turning a 90-degree angle and checking where we came. We were 16 inches off the other pedestal. Yeah. So my track record is intact. I've never been on a construction site where all the anchor bolts were set properly. Now, the thing about that though is it's 104 feet across, and we're off by 16 inches. Anybody got an idea what that translates into as far as angle? That's only 3/4 of a degree. Okay, so when you look at it in those terms, we're doing pretty good. And the reason that we missed, and I'll be honest with you on that one, is we got in a rush with these guys. Okay, we got them placed right, and then when you start putting the concrete in, we're putting the concrete in from one side. Okay, and we're using a vibrator. Fortunately, we had a vibrator. That made all the difference in the world because we've got good quality concrete out there. We use a vibrator to consolidate the concrete, and you can move it around a little bit. Oh, with the total station? Oh, it's probably less than a second. It's really, really good. It's 5 second instrument. Okay, 5 seconds. Okay. Anyway, it's really good. So that's like, I don't know what fraction of a degree that is, but it's pretty small, 1/360th or something. But in this particular case, when we poured the concrete in here, we had to move it down, or maybe it's the other direction. Anyway, we had to move it from one end to the other, and that concrete tended to move the bolts. Okay, so we were constantly pulling them back, hammering them back into place, and all that. And that's where that error came from. And to be honest with you, I'm thankful that we're only off by 3/4 of a degree. So, but the good thing is, knowing that ahead of time, we can accommodate that. Okay, for example, that 3/4 of a degree, if I've done my calculations right, all we've got to do is oversize the anchor bolts by 1/4 of an inch, and that gives us enough rotation in the system that we can account for that. And anchor bolt holes are typically oversized anyway. They're not quite oversized that much, but that's not that bad. The other option would be to just put the holes in to match what we need. So there's some ways to do that, but knowing that ahead of time is good. Another thing is they're going to need to take the total station with them next time to be able to set those anchor bolts, those base plates. So anyway, that's just a little bit about it. This is looking across to the other side. You can see it's the other foundation is right there, and we're just 16 inches off the edge. Just really bothered me. Okay, now we placed 65 tons of concrete, and every bit of it was done by hand. Okay, now fortunately we had about 60 people helping us, but this is the process of mixing. Back up. Mixing concrete in. Come on, do it for me. Come on, play. Okay, this is how you mix concrete in Honduras. This guy right here, he was part of a Rotary Club group that was there helping us. And he's trying to tell them what they're doing wrong. Wow. That's pretty bad. Hang on. There you go. Okay, so the process, hang on a minute, I'm going to get this one started so it can, the process of mixing concrete, the process of mixing the concrete is like this. You bring in your sand and gravel mixture, and and I forget what the recipe is. There's so many wheelbarrows full to the bags, I don't know. But anyway, you get a sand and aggregate mixture piled up about halfway. You take a bag of cement, drop it on that, break it open, mix it up, bring in some more sand and gravel, put another one on it, break it up, mix it up dry, okay, and then you make a volcano out of it, okay. And these guys the Hondurans were expert at knowing, the water, how to put the water and get it all mixed up completely where you had a really good mixture. The problem is they like to do it really wet, which what does that do to concrete? Makes it weaker, yeah. So we were constantly trying to take the water out. We were adjusting their recipe for it. So I think we got down to where it was for a double batch, you used 5 buckets of water or something. And it made really good consistency concrete. And we've got some we brought back. We're going to be testing. Hopefully it comes out good. I don't know. We'll see. But we need, in fact, I asked them, I said, why do you want to know? It's already there. There's nothing we can do about it. But they still wanted to know whether the concrete was good or not. So that was, we'll find out. We'll find out. I don't know if I want to, but we'll find out. Okay, so the second step in the process was to place the concrete. Now you'll hear the vibrator going here. It makes a ton of racket, but it was well worth it. And then, but everything had to be placed by wheelbarrow or by shovel. And this is just a little example of that. You can see how we had the anchor bolts here. This probably didn't help the placement either because the guys were standing on it. But let's see what. All right, so it was a great trip. Our students learned an awful lot. I learned a lot. We made some really good friends. The guy that's standing on the board there, his name's Julio. He was the go-to guy. If we were doing something wrong, he would come over and show us how to do it right. Okay, and sometimes it was helpful, sometimes it wasn't. But he was really a neat guy. He and I got to be pretty good buddies. He called me Maestro, which apparently is like teacher or something. I don't know. But so he was calling me Maestro, and everybody else was Ingeniero. So anyway, we had a really great trip. It was a lot of fun. If you get to go in August, man, y'all are going to have a blast. It's going to be so exciting. Hope you get to go. Hope you get to get involved with the build here on campus as well. Any questions? Did they do the tower part? Okay, didn't do the bridge though, right? No. Okay. Carter. Yeah. We've got a couple of guys over at Barge Wagner, I guess is where it is, right? Barge Wagner doing the pedestrian bridge design. There's a couple of reasons for that. One is it had to be approved by the authorities in Tegucigalpa, and so that was one. The other is the this isn't like a bridge out in the middle of nowhere. It's over a highway. So there's a lot more liability, potential liability involved with it. So we wanted practicing engineers involved with that. And I don't know exactly. Daniel Jordan may have done most of the concrete work. I don't know. He did the drawings for it, but I don't know how much of the design he did. But yeah, the tower was designed by our guys, I guess. Good, good. Yeah.
So what happens if for some reason one of those bolts breaks?
It's not good. That's a bad thing to happen. We hope we don't have to deal with that. The design, let me see. I can put this up on the board. The design for the bridge is like this, okay? You've got the bridge up here, and it's going to be a truss bridge. It'll look like this. It'll have a zigzag pattern to it. And this end's sitting on concrete, and it's got a slip joint on this end, okay? So it's going to have slotted holes so that this end can expand and contract and move a little bit. On this end, what we've got is we've got 2 steel columns, one on either side of the bridge, and we've got a set of your base plates down here. The bridge is actually going to sit on a cross piece in here in between, and this is going to carry all of the load this way, if there is any, and all the load this way. Okay, so if we lose a bolt, then it's liable to collapse. Okay. Now, probably won't collapse quickly because what we have is also over here, and this is not a part of the structural design, but there's a platform right here and stairs going out this way, and this has got a support coming off of it as well. So in fact, we've actually got a little bit of frame action going here, so but it's designed so that the bolts carry all the load. Okay, so yeah, if we lose a bolt, we're liable to lose the bridge. Not good. Yeah.
Was school in session?
Yeah, it was. It was really cool. Yeah. So they were going to school till noon, and so every morning the kids would be around, and they'd come around. They'd try to speak English with us because most of them were taking English classes. You know, it was fun. The other thing that happened while we were there was that I mentioned some of the guys that were there from a Rotary Club. This is a huge group. It's like 50 or 60 people there that come every spring break, and we met them last year too. Vince Dooley, the coach for the University of Georgia football from forever ago, is a member of that group. And I don't know if you're aware of Georgia football or not, but for some reason, the University of Georgia cannot name their field Vince Dooley Field. Okay, as famous as he is, and as much as people want him to do that, they can't do that. So this Rotary Club has gotten together, and they've built a soccer field on site at the middle school that Gwaltney and I helped lay out. I guess a couple of students helped us too. And they dedicated that as Vince Dooley Field. Okay, so Vince Dooley has a field named after him there. Thursday of this past week, the president of Honduras, as well as the CEO for Honduras Outreach International and a bunch of other folks, were at the school to dedicate the field. So that was a disruption in the middle of all that, but it was kind of fun too, because it was a big celebration. Got to shake hands with the Honduras president and all that stuff. So it was kind of neat. So this is a big deal. This place is Honduras Outreach International is very influential. They've got a lot of good friends in Honduras. They're doing a lot of good work, and hopefully we'll have a long-term relationship with them in the College of Engineering. Other questions? All right, great. I took a lot longer than I thought it would. We'll see you guys. Get involved with the bridge build.